Great. We're going to make a video just on how to do these problems, and mainly it's going to focus on the units for photoelectric effect, photon energy. Photon energy is H times F. So I think the most important thing about a photon is its frequency, because that'll tell you the energy. H is just a constant, 6.626 times 10 to the negative 34. Very small number. That's in joule seconds. So if we multiply by frequency, which is 1 over seconds, also known as hertz, you're going to get joules. So let's say it's like a UV photon, which has a pretty high frequency, 2 times 10 to the 15 hertz. You just multiply those things, and you're going to get the energy in joules. So I'm putting it in my calculator as 6.626 E, that means times 10 to that, it's the second comma button, negative 34, times 2 E, 15, and I get 1.32 E, negative 18 joules. Now, whenever you see these very big negative exponents, you know that's a small amount of joules, right? A little photon doesn't have very many joules. Even a UV photon, it's just one photon, right? One other thing that you probably need to know is since C is F lambda, just be aware that they won't always just give you frequency. They might give you the wavelength, and then they will expect that you can do, instead of HF, HC over lambda, because you just take C divided by lambda and you have F. So you can find the energy from lambda as well. So we're going to keep that in mind. So this is a really small amount of joules. It almost seems like joules isn't the right unit for us to be using, because it doesn't really mean anything to say I have 1.3 times 2 times 1.32 times 10 to the negative 18th of something. That's so small. So we have another unit for energy. It's the electron volt. And 1 electron volt is 1.6 times 10 to the negative 19 joules. So if I just divide this by 1.6 times 10 to the negative 19, I get 8.28 electron volts of energy. So these are both energy units talking about the same thing, how much energy this photon has. One of them is in electron volts, the other is in joules. Well, where did this idea of an electron volt come from? Well, you should recognize 1.6 times 10 to the negative 19. That is the charge of an electron. So remember, voltage was joules per coulomb, right? So if I take the volts times the coulombs of an electron, that should be the joules. So 1 electron volt is the energy that 1 joule would give to that 1 volt would give to 1 electron. Right? That's kind of the relationship. And so we're going to need this because we're going to take these photons and we're going to smack into electrons, and now the electron's going to have energy in the electron volts, and then we're going to use voltage to try to stop them. And so if something had 8.28 electron volts, we would need, if it was an electron, we would need 8.28 volts to stop it. So that's basically the main reason why we want to use this unit. I want to give you one more conversion thing here. So if it was 8.28 electron volts, let's see what lambda was for this 2 times 10 to the 15 hertz. So we're going to take 3 times 10 to the 8, speed of light, divided by 2 times 10 to the 15, frequency. Hopefully you're good at scientific notation, because there's plenty of it in this unit. I've got 1.5 times 10 to the negative 7, right? That is the same as saying 150 nanometers. 150 nanometers has an energy of 8.28 electron volts. So if I take 150 nanometers and I multiply by 8.28, I get 1240 nanometers. And that turns out to be the energy of 1 electron volt. So 1240 nanometers would be the photon's wavelength when it's 1 electron volt. If you're shorter, this one here is 8 times shorter than that, you're going to have 8 electron volts. Right? If you are half of 1240, like let's say 620, that's half of 1240, you'll have 2 electron volts. It's hard to get your brain around this, that as the wavelength gets shorter, you get more and more electron volts, but a shorter wavelength means a higher frequency. And the higher the frequency, more energy for photons. Okay, so let's talk about the next concept, which is stopping potential. Right, so let's say that I had taken this photon, smacked into an electron, and now the electron has some of those 8.28 electron volts. Let's say it didn't get all of them though. Remember, there's this thing called the work function. So when you have your electron sitting here in the metal, minding its business, and in comes a photon and smacks it, the photon doesn't give all of its energy to the electron. Some of it is needed to just kind of like pry it out of the metal, which is called the work function. So we had 8.28 come in, and then let's say the work function was 5 electron volts. Then the electron would leave with 3.28 electron volts. Right, so my electron's leaving, and let's say that I have it leaving and I want to try to stop it by applying a voltage against it, like so. If I want to apply a voltage against it to get that electron to stop, so here's my electron moving along, and I'm going to try to stop it by using a negative to stop it, I need to use 3.28 electron volts to get that thing to stop. Or I'm sorry, 3.28 volts because it's one electron, and that will stop it. And so the stopping potential is 3.28 electron volts. Right? Well, how many joules is that? Well, 3.28 electron volts is going to be way less joules. So what I need to do is multiply by 1.6 times 10 to the negative 19. Remember that 1.6 times 10 to the negative 19 joules is equal to 1 electron volt. Right? So if I had 3.28 electron volts, then I have 5.248 times 10 to the negative 19 joules of energy. What kind of energy does the electron have? Well, it has energy of motion, of kinetic energy. So you could say 5.248 times 10 to the negative 19 is equal to 1/2 mv squared. Well, I happen to know m for an electron. It's 9.11, number, times 10 to the negative 31st kilograms. Very small. So if I wanted to get the speed of this thing, I can do that too right now. It is moving at 1,073,378 meters per second. And so just a measly 5 times 10 to the negative 19 joules will give an electron moving that fast. Right? It's 3 volts that you would apply to an electron to give it that equivalent energy. Or it would take 3 volts, 3.28 volts to stop that electron. And so these are all ways to talk about the energy of the photoelectrons that are knocked out by the photoelectric effect. And the last thing that I wanted to talk about was the work function and the threshold frequency. So remember I said, okay, it takes 5 electron volts to pry it out of this metal. Every metal is going to have some work function, some energy that is going to be used just to get the electrons out. And then the remaining energy will be given to the electrons. So for example, for this metal, you needed 5 electron volts just to knock them out. So if the incoming photon, instead of being 8.28, had been like 4.28, no electrons would have left. You have to be at least 5. That's the minimum energy you need. So let's see what frequency 5 electron volts corresponds to. Well, what I could do right now, if I wanted to do a lot of work, is I could turn the 5 electron volts into joules. Right? You know how to do that now. Then I could divide by H, because E equals H/F. And I could get a frequency, the threshold frequency, the minimum frequency to knock out an electron. But an easier way to do this problem is just knowing that 1240 would be 1 electron volt. So if I take 1240 and I divide it by 5, it takes 248 nanometer light to knock out an electron. Anything longer than 248 will not work for this metal. The 248 is called the threshold wavelength. Okay, what's the threshold frequency? Let's take the speed of light, 3 times 10 to the 8th, and divide by 248 nanometers. Now remember, nanometers is times 10 to the negative 9. So when I do that, I get 1.21, let's say, times 10 to the 15 hertz. That's the threshold frequency. Right? So we're talking about the same photon here. It's either 248 nanometers if you're talking about its wavelength, or 1.2 times 10 to the 15th hertz if you're talking about its frequency. And what is the work function? The work function is the energy that corresponds to that frequency. Right? We said it was 5 electron volts. Right? Where do you get that from? Well, if we take 1.21 times 10 to the 15th, you multiply by H, you'll get joules. And we take that joules, divide by 1.6 times 10 to the negative 19, you get 5 electron volts. Or you could take 1240 over 248, you can get about 5 electron volts. Right? So you got to understand, work function is that minimum energy to knock out an electron. And then whatever energy you have above and beyond that is what you will give to the electron, and then you could use voltage to stop it, called stopping potential. All right, that's pretty confusing, but as you practice these problems, I think you'll get the idea what's going on.